So, continuing lecture 5, dealing with beams, simply supported beams that are variously loaded. This time we're looking at cantilevers. We want to look at cantilevers. Cantilevers are beams that are supported at one end only. Other beams, simply supported beams we have been dealing with, were supported on both ends. And as such, the two supports carries the load. The two supports carry the load. The load is sent to both supports. But in this case, when the only one support is carrying the structure, only one support A, the whole load is carried by A. The whole load is carried by A. In this cantilever, the whole load is carried by A. The cantilever that has a support helping it, like support B in this one, is called propped cantilever. We're not talking of propped cantilever because by support this support B, this cantilever, this structure is already indeterminate. I will go to that. We've not gotten to that, so I don't want to carry you to where you have not gotten into. This one is a cantilever, but propped cantilever. It is indeterminate, so we leave it. We'll get to it. But now these are ordinary cantilevers that are determinate as we are walking. This cantilever here carries a uniformly distributed load. This one carries a pointed load. A cantilever has only one support. This type of cantilever has only one support, so the whole load are on that one support. So we don't need this time to start looking for reactions because we already know the reaction. The reaction is the load because there's only one support that is carrying the load. So the reaction of that support is the load. Here, the reaction here is 6 times 8, which is 48 kilonewton. That's the reaction at A. There's no reaction at B because there's no support at B. In this case here, the reaction is 7 times 5, which is 35. 35 kilonewton is the reaction at A. So we don't need to start calculating reaction. But if it was in the other beam that has two supports, we don't know what is the reaction in A or B until we calculate. So in this case, the one support alone is carrying the load. So since we have known the reaction here, in this case, reaction at A in this case is equal to 48 kilonewton. Then it's simple. So to take moment, to get the moment, reaction here, reaction in this one, RA is equal to 35 kilonewton. So to get the reaction now, this one we're keeping this till when we do indeterminate structures. So to deal with this first one, now to get the reaction, to get the bending moment, at this A, at point B here, bending moment is 0. Moment at B in this case is 0 because there's not even a support. There's no support. We are moving from B. There's no support. Where there is a moment is at A because if you watch support A, is the support type of support that resists moment. There's no support in B, as a matter of fact. But at A, the type of support is the one that resists. So the whole moment comes to BA. Is resisted at A. So to calculate that moment that is being resisted at A, to calculate it, we have the M at A is equal to, the M at A is equal to the load, because moment is conversion of load to moment, which is load times perpendicular distance. The load here is 6 kilonewton per meter. To get it as a collection of load, because it is 6 kilonewton in every meter, and there are about 8 meters. So to get it as a collection of load becomes 6 times 8. 6 times 8 minus 6 times 8 as a collection of load. Now to get it as a moment, we now multiply with the distance from the perpendicular distance from the center of gravity, which in this case is half of 8 times 8 over 2, which is 4. That means 6 times 8. 6 times 8 times 4. 6 times 8 times 4. That gives me 192 kilonewton meter. 6 times 8 times 4, 192 kilonewton meter. 192 kilonewton meter. That is the bending moment. Minus 192 kilonewton meter. Minus, but if it is minus, because if I take moment, it's turning the same. The moment is turning this way. If it's turning this way, looking at where I started, at B, the way I normally talk, at B, I have I call it positive. That means the load is also turning the same way, because look at the line of action of the load is turning the same way. So it will be plus 6 times 8. 8 squared. That is, look at this, 8 squared over 2 equal to 0 for that point. The point MA at point A to be in equilibrium. That means MA is equal to, that's why the sign changes to minus when it crosses the sign of equality, to 6 times 8 squared over 2, which I got to be minus 192 kilonewton meter. That's the bending moment that's the bending moment. So we have gotten the reaction, the bending moment. The same way, the shear force from here is the load. At this point, the shear force is 0 at B. The shear force is 0. So the load is negative until it gets to, the load will now be, it closes here, where 6 times 8, that's the total load. 6 times 8 minus the reaction. With reaction is 48, and that's 6 times 8 in my, for the reaction. The shear force also closes at that point. So the bending moment diagram, to get the bending moment diagram, look at the structure. If you check, the bending moment at B is 0 at this point. The bending moment at A is minus 190. So, and it is quadratic. If you check 8 times 8, 8 squared, the equation is quadratic. And a graph, because bending moment diagram, as I said, is a graph of load against distance, perpendicular distance. And every quadratic equation, the graph is a curve. So this is the bending moment diagram. That's the bending moment diagram. That's the bending moment diagram. So as we said, the shear force at this point is 0. The shear force at this point is 192 kilonewton meter. So the shear force is this way. Here the shear force is 0. At this point the shear force is 48. So this is negative shear force, which is 48 kilonewton. That's the shear force diagram. So I've gotten both the bending moment and the shear force, or the reaction A, if one wants. So the next one, this one, here, the same way I was talking about, the bending moment at B here is 0. The bending moment at B is 0. Bending moment at B is 0. So to get the bending moment at A, where there is really bending moment, is M at A 5, because the 5 is being made a moment. 5 times 7, 5 times 7, the making the load, which is 5 kilonewton a moment, multiplying by perpendicular distance, which is equal to minus 10. 5 times 7 minus 35. Minus 35 kilonewton meter. Minus 35 kilonewton meter is the bending moment. So the shear force here, is minus 5. Shear force at this point is minus 5, and the same shear force moved and get to this point where reaction A is equal to 5. Oh, sorry. Reaction A is 5, not 35. Reaction A is 5, sorry. Reaction A is 5. It's not 35. Reaction A is 5. Sorry, reaction A is 5. Reaction A is 5, but the reaction is equal to the load. Because there's no other support. The reaction is equal to the load. The reaction is equal to, the reaction here is equal to 5. The reaction here is equal to 5. So the shear force diagram, this is minus 5, which continue gets here, meets 5 and closes. So the shear force diagram will be like this. 5 minus 5 and continue. Gets to 5 here, which neutralizes to 0. So that is the shear force there, which is 5 kilonewton, 5 kilonewton. Bending moment diagram here. This is the, look at the bending moment diagram. It's minus 35. It is 0 bending moment at this point, minus 35 at this point. And it's not a quadratic function, it's linear. It's linear. It's linear. This is 35 kilonewton meter. That's the bending moment diagram and value. And this is the shear force. Shear force is 5. The reaction here is 5 kilonewtons, not 35. It's 5 kilonewtons. So we have been able to get both the reaction here, the bending moment here, the shear force here. And in the same way, we have been able to get the reaction here, the shear force here, the bending moment here. So that is how to calculate bending moment shear force for a cantilever. No matter how it is loaded, even if it's loaded triangularly, we will get to that one now. We will deal with that. So that's the end of this episode. Thank you.